Okay, welcome back. I hope you did all the exercises I set you in the first section on tensor products to get some practice. And now on the second section, as I already wrote down, we'll get some basic properties. So we have the assumptions as before: R is a ring with one, R is not necessarily commutative, and have the right module, the right R module A and the left R module B. So let me start with a proposition of a property. First. If I look at the map, so this is the map of sets basically. F from A cross B to the tensor product A tensor RB. Okay, so here I had an element A comma B, and I map this to its class in, well, this was a quotient of ZA cross B, free within group on A cross B, and that was denoted with A tensor B. And this has a few properties, and one says bilinear. This may be not an ideal terminology. So if you look in one of the other sources I quoted, one sometimes also says this is R balanced or middle linear with respect to the ring R. So what do we mean by this terminology? Well, it has three properties that we simply imposed. Okay, if I look at f of A plus A prime comma B, well, this will map to A plus A prime tensor B, but I could work this out, because that was the first relation I imposed, into A tensor B plus A prime tensor B. And that is then the same as f of A comma B plus f of A prime comma B. And again, this holds for all AA prime in A and B and B. And similarly, the relation I impose in the second coordinate will tell me that f of A comma B plus B prime is the same as f of A B plus f of A comma B prime. And then there was a third type of relation. Okay, so f of A R comma B, where now R is in the ring R. Well, I could move this R over this tensor sign, that's called, and then I would do the same thing. So that's the same as f of A comma RB. Okay, so by construction it has this property, and well, the tensor product is basically universal with respect to this property. So let me have a proposition. Okay, so the tensor product was in the Abelian group, and we're going to, in some sense, compare it with any Abelian group. So if C is any, well, I said I will be saying Z module, so let me write Z module for Abelian group. And have any map phi from A cross B to C. So if this one is bilinear, so that means it will satisfy those properties 1, 2, and 3, but then with f replaced with phi, and that makes sense because the only thing I needed was an addition, and I have this in the Abelian group. So if I map phi from A cross B to C using with those properties, then there exists a unique group homomorphism. Okay, the f and the phi is basically no structure because they don't say anything about addition really in if we read, because A cross B has no addition structure in a nice way. And that means not the standard one addition in every coordinate. But C has this property. So there is a unique group homomorphism phi bar from the tensor product to C with phi bar after f equals phi. Okay, so I can basically get my phi from the f and the new phi bar, and of course, more standardly, one says that the diagram so I can go from A cross B, have this universal map, I claim it's universal to the tensor product. Then I've been given a map phi to C from A cross B with a few properties, and then we're claiming that there is a unique map here, phi bar, such that this thing commutes. A visual statement of what is going on. Okay, so let me prove this. So suppose that phi bar exists, and well, let's see what we know about it. Phi bar, of course I know phi bar if I know what it does in generators because it's a group homomorphism, so I don't need to check what it does in generators. And well, this is phi bar of f of a comma b, a definition of f. And oh, this is the composition phi bar after f on AB. So if I want to have this property, then we must have that this is phi AB. Okay, phi is given, so that's our only candidate. So if it exists, it will be unique. So we now have to construct it in order to check it really exists. So for that, you start with, well, not with the tensor product because that's a complicated thing. You start with a nice generator. So you start with the free being group on A plus B. So you say that the group homomorphism from Z A cross B, so find B the free being group on A cross B. So I want to create a map to C on the tensor product, so I start with this one, and I'm going to map, well, if you want, I take n times A comma B, or just to generate AB to phi of AB. Okay, that's the only thing that we could have, because if we are going to factorize this thing through the quotient, which is the tensor product of A with B over R, then this is what is dictated here in the end. A tensor B, which will be the class here, would map to that one. And then you check that this one, if I write it out, well, the tensor product had three relations I imposed on this thing. The first one was that A plus A prime comma B would be the same as A comma B plus A prime comma B. So, but if I put phi on this as opposed to f, then this, well, and with a minus, so phi of A plus A prime comma B minus phi A comma B minus phi A prime comma B, that's the image of one of the relations. But we assumed by the first property of this phi being bilinear, that this would be 0. So it would kill the first relation, this map. It would similarly kill the second relation because we assumed this one for phi, and it would kill the third relation as well because of that one. So this one descends to a morphism or a group homomorphism on the tensor product by the check I just indicated. So let me just say because of the properties, because the properties of phi kill the relations imposed on Z AB. Okay, so this construction we impose those relations and we simply assume that it works. Now this is exactly the correct map. So because this descendant map, so this gives a map from the tensor product to C. And well, it maps A comma B to phi of AB, but now A comma B has mapped to the tensor product AB. This is mapped to phi of AB. So it not just gives a map, sorry, it gives me a group homomorphism. And that is phi bar. Okay, and because it, well, I did it on generators, but of course, phi being group homomorphism is a linear. So that means that if I take a sum, so let me just say that is a remark, so that constructs phi, so a little remark. So if I take phi bar of a tensor product, so this will be a sum of AI tensor Bj, finite sum over some I and j, and then, well, it has to be a homomorphism. And if you like, you can also put integer coefficients in front of this, but they would just come out, and that will then be the sum I and j of phi AI Bj. Okay, so that's the explicit formula that comes out in the end. Okay. So, in some sense, you could use the property in this proposition, which I'm erasing, to define the tensor product in a more abstract way, because you could look at all the abelian groups C together with the map, the bilinear map from A cross B to C with the properties, and then there is this unique, up to unique isomorphism, universal elements for this property. And that will be the tensor product. So that will be a categorical way of constructing this thing. Of course, it doesn't tell you it exists, but it tells that if it exists, it is unique up to unique isomorphism. And the construction we had was just writing this down explicitly. So both approaches are valid again, but maybe for the first time it is better to see an explicit construction. Okay, that is one important property. So let me now say a little break with the previous for other properties. What happens if I try to change my modules A and B? Okay, so suppose I now have a map 5 from A to A prime, and suppose this is a morphism of right R modules. Now, I suspect this wasn't defined before, because I talked about left R modules, but it's homomorphism of abelian groups that commutes with the right multiplication under R. So the important thing is that if I take phi of AR, that will be the same as phi of A times R. Okay, so just like a left morphism of left R modules, but of course everything with R is now on the right, but the R still has to come out. So if I have this one, and I want to do something for the B, so there will be psi from B to B prime. Okay, so here A and A prime are both right R modules. Here they will be both left R modules. So if this is a morphism of left R modules, well, then I would like to get a morphism from A tensor over R with B with A prime tensor over R with B prime. Both tensor products exist, and we're going to construct that. So we get and in general this will be a group homomorphism because the tensor product is only an abelian group. So A tensor over R B maps to A prime tensor over R B prime, and it as follows. Okay, so we want to use this universal property. If you want, you can also just write down in the end what comes out and and go through the details. But this universal property basically is there to save you some work. So we start with the map gamma from A cross B to, well, in the previous proposition I need a map from A cross B to an abelian group. So the abelian group will now be A prime tensor over R with B prime. And I'm going to map the generator of the element AB to, well, I can't map it to A tensor B because that will be in the wrong tensor product. But if I take phi of A, being A prime, and if I take psi of B, being B prime, and if I take the tensor there, this will be okay. And then you have to check that because of the properties of phi, that this is bilinear. In the sense that I erase there, but it has to have the three properties. So it's an exercise to check. So by the proposition, I get a map gamma var, and that will be this one, but one normally writes it as phi tensor psi. So it will use a map phi tensor psi from A tensor R B to A prime tensor R B prime. And well, what did it do? It basically said if you map A comma B to this, then in the tensor product you should map A tensor B to this. So it will map A tensor B, a generator, to phi A tensor psi of B. Okay, so that's a very explicit formula. And well, to make a link with functors, which we didn't really mention until now, well, it's a bit annoying because basically this one has two arguments, so A and B, and it's mostly varying both. So let us simplify things a little bit and fix either A or B. Okay, so in particular, well, if I fix A or B, then I have a natural map from A to A, the identity, and similarly for B. So using phi is the identity on A, gives map it A tensor psi from A tensor over R B to A tensor over R B prime. And that is one case, and of course I can also use psi to be the identity in B. So this gives phi, so this will be an arbitrary phi again, tensor identity B from A tensor R B to A prime tensor over R B. And it does what you think it does, because if you look at the formula, you would, in this case, apply the identity on A. In other words, you're not seeing that. You just apply your psi in the second one, and similarly in the second case. And if you now do some checking, how this behaves if I say fix phi to be this one, and I take two psi's, so B to B prime to B double prime, you see it behaves very nicely because you're just composing the respective maps you have in the second coordinate, and similarly for this one in the first. So this gives covariant functors two of them. I can fix the A and then put an argument B, so that will have to be a left R module in the second, and then I go from left R modules to Z modules to being groups. And similarly, if I fix my B and then let the A run, so now I have to plug in the right R module and again I end up with the Z module. Okay, so again, it's a very good exercise to check this to make sure you get through the notation that is involved. Okay, so then there is one more property that I would like to state, and then I'll again give a few examples that will probably help you to figure out why on earth this tensor product is useful, because that has well, hasn't really received that much attention yet. Okay, so for the third property, we'll formulate a proposition. And suppose that I assume my A is going to be a direct sum of right arm modules. So let's just you do everything coordinate-wise, and if you multiply on the right by r, you multiply in every coordinate. It could be finite, but if this is a big sum, then you would have only finitely many coordinates not equal to 0. And I can do something similar for B. So this would be a big sum maybe of bj's, and this will now be a direct sum of left arm modules. And then I claim that there is an isomorphism. So we have this tensor product. On the other hand, I'm going to build the right hand side. AI tensor Bj over R also makes sense because AI is a right arm module and Bj is a left arm module. And then I can take a big direct sum of those by letting I and j run over the indexing set. And then I claim that there is an isomorphism between this as attributes. In other words, tensor products commute with arbitrary direct sums in both positions. That's what it says in words. And to write it out in glorious detail is a little painful, so my approach will be to indicate what the map is, and in both directions. I'm going to leave some details to you. So, proof. I'm going to apply the previous one basically, because if I, for example, go from A and I project to a particular coordinate AI, that's a map of right arm modules. Okay, so the projections from A to each AI, and also I want to go the other way around, so I'm going to write the inclusions AI to A, so I stick AI into the ith position, so to say, and the rest I make 0. Say those are morphisms of right arm modules. Well, that's the story for the A, and of course, you have something like this for the B. So similarly, let me be slightly shorter. So I map here projection B to Bj, and the inclusion Bj to B are morphisms of left arm modules. So I'm in the situation of the previous properties that have morphisms on the A and the B, and we can apply this. So we get out of this group homomorphisms. A tensor RB to each pair AI tensor R bj, and this map is very simple because it basically said that you have to apply your projection in the A position here and also in the B, so it's a very explicit and simple map. But also the other way around, AI tensor over R bj to A tensor B over R. So the AI goes into A, you put in some zeros, so to say, and the same in the second position. Also very explicit map. But this is not yet what we want, because we want to have this big direct sum.
So before you erase the left-hand board, so we've had a couple of properties which have concerned various things as Z modules, but presumably in the commutative case we can upgrade all of these to categories of R modules and isomorphisms of R modules?
Yes, if you have more structure, and I've been avoiding this because one can say an awful lot more, but indeed if your tensor product has more structure, then a lot of those maps will have more structure. So indeed, for example, if R is commutative, so this is in a very natural way going to be an R module, then, well, everything becomes a homomorphism of R modules. Similarly, if A happens to be an SR bimodule, you get blah, blah, blah. And of course, you have to assume those are, okay, I don't want to say anything about this because it's very similar. And I think once you understand sort of this basic case, and you understand how additional properties go in, it's very easy to see that basically everything then works in a more general context. But I think for a first introduction, it's just too annoying to go through all the somewhat painful details. Okay, I hope I can now erase this blackboard. Okay, so I have maps of repeating groups in my context of Z modules. And now you then just combine them. If I have this to here, then I can sort of the direct product of those maps, and then I end up in the direct sum. Because for every element I have only finitely many generators in an expression, and in each generator only finitely many AIs will get a non-zero contribution. Same for the BJs. And therefore, if I take the product, I go from A tensor R over B to this big direct sum. And also the converse. So here, if I take AI tensor over RBJ, and I want to then, well, I'm going to be forced to take a direct sum, because if I combine this, and this is just basically the sum map. I take every component here and I put it in there. If I take a direct product here, then I cannot take the sum that I will have to take, because I can here take only finite sums. So here you could take the direct product, but that would be too big, because you land in the direct sum. You know, there's very explicit maps, and then I'm going to leave it to you to check. Those are, well, we know that there are Z module homomorphisms, so that's okay, and those are each the inverse of each other. Okay, so I'm going to finish this thing with a few exercises. So, sorry, first exercise, carry out this check in detail. And we'll do this in general by using generators. Okay, you have to be a little bit careful, because there is a little bit of notation that is hidden. If you really work it out, you'll see that this is maybe not quite as simple as you might think in first glance. But it's a good exercise to get around things like this. And the other exercise is the one I've given before at the end of the first section. So exercise we do, hopefully, or do, that we have an isomorphism Z module MZ, tensor over Z, Z module MZ isomorphic with Z modulo GCD M and Z if we have M and N arbitrary inverse. If M or N equals 0 or 1 or minus 1 or so, that doesn't really make any difference. But in this case, if M and N are both non-zero and not plus or minus 1, you can now use the Chinese remainder theorem to decompose this into primary parts, and the same thing here, and you can actually use this direct sum proposition. It gives a little bit more insight. The result will be the same, but it becomes more explicit than what you may have found before. Okay, I'm going to finish with a few examples, very much needed by now. So, for one thing, if R is in any ring, well, with 1, narrow convention, and I start taking direct sums, so I can take R to the power m, and that is automatically a right R module, and R to the power n is a left one. Oh, but I can view this as a direct sum of n copies of R, and same thing with n copies of R in the second. So by what I've just been stating, this will be the same as R tensor over R, R, and then n times n copies. I get n copies of the index in the first one and n in the second, and in total I have n copies. And this is an example we could simplify. So this will be isomorphic to R to the power n. And it's a good exercise to follow along what the maps are here to make sure you really understand. So in general, this is an isomorphism of Z modules. And let me just say that if we assume that R is commutative, and a very important case here is the case R is a field, this is up to isomorphism, arbitrary finite dimensional vector space over that field, same thing here. And then you can see, well, the dimension here will be an n-dimensional vector space tensored over the field with an n-dimensional. And if you then look here, it's going to be dimension n. And let me just say this as R modules. If R is commutative. So that is one thing that you may see, and then the other one is what is called extension of coefficients. That will be the final example. And suppose that I have a ring homomorphism. And let me call this F. So F goes from R to S. This is a ring homomorphism. And in our convention, we always assume that it maps to the 1, so let me make this explicit. Then S is a left R module. So I have to take an element in S, and have to left multiply it with an element in R. And the natural thing to do, first apply F to R, and then happily multiply the thing in S. And you can check, this makes S into a left R module. And it is also a right R module. Try, well, do the same thing on the right. S times R is S times F of R. And those actions commute. In fact, this is an RR, S is now an RR bimodule, if you want. Anyway, you can say it's either left or right. And for example, so if I take R to the power n, which I can view as a right R module, and I can now view S here as a left R module using this map F, and you can then check. Well, first thing is it is an isomorphic to R tensor R S to the power n. Okay, this is basically decomposing this in all the components and then taking the tensor product in all the components. And this one you've seen before. this is going to be isomorphic to S in each part, so this will be S to the power m. So this is if I put the S on the right, and I can also put it on the left, because S is also the right R module, and then you get this one by decomposing in every component, and again this will be isomorphic to S to the power m, and both are as Z modules.
Well, but also as S modules, right?
In fact, I was going to say it actually has a lot more structure. At the moment, from what I've been saying, it is only a Z modules because I've been basically ignoring it. But I've already indicated that if, for example, S is an RR bimodule, and in fact, you can also make it is even an RS bimodule if you like. Indeed, this, if you view this thing as an RS bimodule, so R acts on the left on S through F, and on the right by just natural multiplication, then this would be an isomorphism of right S modules.
Yeah.
And similarly here, if I view this as a left S module and right R module through F, so it's an SR bimodule, then this will be an isomorphism of left S modules. Okay, so this is the kind of argument we could often give if the things have more structure, but as I said before, first exposure to this kind of thing is probably best to ignore it and then maybe go back later and see that indeed, yes, fairly clearly things have more structure. Okay, thank you for your attention.